since we learned activity, okay, and then now um, calculate the pH, okay. pH, as you know, is defined by the negative logarithm of proton concentration, but using activity. So new definition is like this, okay. pH equals minus log of proton activity, and using activity coefficient and molar concentration, it can be rewritten as this one, okay. And the purpose of this calculation is to see how how much this activity affects pH calculation, okay. For example, here the example 1 is the pH of pure water at 25 degrees C. Since the protons and hydroxide concentration is so low, it is equally dissociate, and it makes the concentration of these two species are equal, which is 10 to minus 7 molar. At this low concentration, activity coefficient is nearly 1, okay. And since this is nearly 1 and pH is 7.00, okay, there is no problem at this for this pure water. But problem arises when we uh, consider the pH of this water when this potassium chloride this salt dissolves, okay, under 0.1 molar potassium chloride solution. And then first we have to calculate the ionic strength of uh, this solution, okay. But there is another way here. There's from this Kw, right? This is the water dissociation constant, yeah, is actually defined by this using this activity, okay. Here activity of a proton and activity of hydroxide ions, okay. Then it can express by this molar concentration, okay. And since the ionic strength of the solution is 0.1 molar, right? From the table we got activity coefficient of proton, which is 0.83, and activity coefficient of hydroxide ion, okay, which is 0.76. All right. And then from this equation we calculate the molar concentration of X of proton and hydroxide ions, okay, using this one, which is 1.26 times 10 to minus 7 molar, okay. This is a molar concentration of protons and hydroxide ion under this condition. One thing you have to keep in mind is that these Kw values, they are always constant, okay. And now this part is only changing, okay. And what is the pH? Using this pH definition, okay, this activity of a proton equals molar concentration of proton and multiplied by this activity coefficient, okay. Here the proton concentration is given here, and then proton activity coefficient is 0.83, and activity of a proton under this condition is 1.05 times 10 to minus 7, okay, not much different from 10 to minus 7 molar, okay. And then pH is calculated to be 6.98. You see, what's the difference? Difference is only 0.02, okay. So regardless of using activity coefficient or not, okay, the pH doesn't change much, okay. The change is only 0.02, okay. But this calculation shows the how this activity affects, in this case, pH. All right. Now we enter a very important section. In this section, we know you learn the systematic treatment of equilibrium. Okay. In analytical chemistry, you have to calculate many things, okay? And you have many equilibriums, many reactions, yeah? And many species are involved in the reactions. And how do you calculate each species concentration? Okay, but there is a very important fact is that there is only one uh, solution. Okay, once you for example the dissolve a salt, okay, and then you want to calculate the solubility of the salt, okay, but when you prepare a solution, okay, the solubility is given only one value, okay. For the same solution there cannot be mm, two solutions, okay, which means that the you can, by principle, you can calculate the solubility, okay? In other words, the number of unknowns must be equal to number of equations, okay. Since you prepare any solution, yeah, that's it. There is only one condition, okay. But question is, how do we find number of equations, okay. So in the case, we need some techniques, okay. First, there are two equations: charge balance and mass balance equations. Charge balance equation is what? Since the solution is neutral, okay, which means sum of positive charges equals sum of negative charges, okay. This is a charge neutrality condition, right? And also there is a mass balance equation, okay. From the first law of thermodynamics, mm, the the mass, or the principle of law of mass conservation, no mass is created or no mass is destroyed. So the mass balance should be hold, okay, mass balance. And from the charge balance you obtain one more equation, only one more equation. But from mass balance equation, okay, you can get sometimes only one equation, or sometimes you get two independent equations, okay. And still you need more equations, yeah, from the equilibrium constant, yeah? There must be an equilibrium constant, so total number of unknowns must be the same as number of equations. So under this condition there is only one, yeah? Only one solution, yeah? Okay, practicing to write charge mass balance equation is important. You see, writing a charge balance equation is very simple, yeah? It is very simple, okay, but writing mass balance equation is not that simple. So you need practice, you need practice after practice, okay. So solving, yeah, in principle you can solve the equation because the number of unknowns is the same as the number of equations, but actually solving is different. Sometimes you need to use spreadsheet like Excel, yeah, for the numerical solution. All right. Okay. Yeah, let's take an example. The one simple example is the this one mixed solution, 0.0250 molar potassium dihydrogen phosphate and 0.03 molar potassium hydroxide. The question is write a charge balance equation. Okay, charge balance equation, and now you list the positive cations and anions. Okay, there are only two cations: potassium ion and proton ion. Okay, but there are 4 anions: hydroxide anion, and this one dihydrogen phosphate, and monohydrogen phosphate, and phosphate ions. Okay, no other than that. Okay? So charge balance means what? The sum of positive charges is equal to sum of negative charges. Okay, what's the positive charge? These two. Okay, here um, on the left side you write the cations concentration, proton and potassium ion, equals on the right side negative on the charged species. Okay, hydroxide, and this one, okay, dihydrogen phosphate, and this one, yeah, monohydrogen phosphate. It is divalent. Okay, divalent. So one species takes two negative charges, so you have to multiply by 2. Likewise, for the phosphate ions, you have to multiply by 3. Okay, this is the charge balance equation. Okay, actually very simple. Right? And this figure illustrates, okay, by the bar graph. Okay? Here, proton ion concentration is too little. Okay, actually, this one is the actual values after calculation. Okay, proton ion concentration is too little. 5.1 times 10 to the minus 12, right? It is not shown here. In the meantime, potassium ion concentration is what? Immediately we can say here. Okay, potassium ion is is diluted. Okay, by this one. So it is. I'm sorry. It's actual in the after solution. Yeah, the final potassium concentration uh, is there is two contributions from this species and this species. Okay, since they are completely dissociated. Okay, potassium ion here from 0.25 plus here 0.03, which is 0.0550 molar. Okay, this is potassium ion concentration. But what about the hydroxide ion concentration? Okay, it is not simple. Okay, it is not simple. So you have to calculate, yeah, using other equations. But at this point, it is enough to see this one. Okay, and then you add this potassium ion concentration plus proton, right? The two small. Okay, so left side, this total cation concentration is about 0.055 molar. Okay, what about the on the right side? This one 0.002 plus this one, this much, and this one multiply by 2. You have to multiply by 2, and this value multiply by 3, and then you get this one exactly 0.055 molar. Okay, now there are several examples for practicing mass balance equations. First one is simple. Okay, 0.05 mole acetic acid in water to give a 1 liter solution. So this one, the acetic acid analytical concentration is 0.05 molar. Okay, but it undergoes dissociation. Okay, and then after dissociation, it takes two forms: dissociated form and undissociated form. Two forms. Okay, and then this total concentration equals, you know, to equilibrium concentration. Okay, you see this bracket concentration is called equilibrium concentration. All right, this is a mass balance equation for this solution. And let's keep going. Let's consider 0.025 molar phosphoric acid solution. Okay, which means that 0.025 mole of this phosphoric acid in 1 liter. Okay, so total concentration of this phosphoric acid, this one, this is called analytical concentration, 0.025 molar. And then What is the contribution? This phosphoric acid, now after dissociation, it becomes this one, dihydrogen phosphate ion and monohydrogen phosphate ion and phosphate ion. And also there are non-dissociated phosphoric acid. Okay, so this total concentration equals the sum of all these four species concentration. Okay, yeah. You must not be confused at this one. Okay, yeah, all right. And what about this mixed solution? In 1 liter solution, there are 0.025 mole of potassium dihydrogen phosphate, and this is the same as the previous one, 0.03 mole of potassium hydroxide. Okay, in this case, we can write two mass balance equations. First one is for potassium ion. Okay, since they are completely dissociates. Okay, potassium ion concentration is the sum of this one from here, and the other one is from this species. Okay, which is 0.0550 molar. Okay, but what about the phosphate ion? Okay, in this case, although we start from dihydrogen phosphate, anyway, it dissociates in water, and it takes 4 what species. Okay, so some of these 4 species, the concentration is this is 0.025 molar. Okay, this is another mass balance equation in this case. Okay, don't be confused at this. Okay? And this one, yeah, this is the last no last one. What about the lanthanum iodate? Yeah, this lanthanum iodate is a very insoluble um, species in water. Anyway, it dissociates into lanthanum trivalent ion and 3 iodate ion. Okay, from this equation we can get mass balance equation. Okay, so this one, iodate ion concentration is 3 times larger than this lanthanum ion. So this is a mass balance equation. Okay, in this case, but very unfortunately, there are another lanthanum species or this iodate species. Okay, not only this one, but also lanthanum iodate, yeah, and lanthanum hydroxide ions are there. Okay, how do you deal with these two species? So the idea is that we start from here. Okay, total iodate concentration is 3 times of total lanthanum ion species. Okay, concentration. So what is the total iodate species? This one and also this one. Okay, there are 2 species, yeah, that contains iodate. Okay, so iodate concentration plus lanthanum iodate concentration, yeah? This equals 3 times of total lanthanum species. In lanthanum there are 1, 2, 3 lanthanum species, right? And lanthanum, pure lanthanum species, and this one. Okay, and this one. Okay, yeah, this is the mass balance equation for this lanthanum iodate case. Okay, this is a little bit confusing. All right, yeah. But when the total concentration is unknown, you need another practice. Okay, mass balance when the total concentration is unknown. This is example. Okay, silver phosphate. This one. This is very insoluble, right? So the case is the same as this one. Okay, yeah. Silver, since when it dissolves, one species now makes uh, one phosphate ion and 3 silver ions. So silver ion concentration is 3 times larger than phosphate ions. Okay, but this phosphate ion undergoes the reaction with water, so it makes 1, 2, 3, 4 species. All right. In this case, we start from this equation, and then instead of this phosphate ion, and then we consider these all phosphate containing species. Okay, so this is the correct mass balance equation for when the silver phosphate is dissolved in water. All right, yeah, that's the idea.